This video is going to be on how to find the arc length, which if you guys don't remember what that means, that's the length of a curved line as opposed to a straight line. So to start with, we're going to remember how we find the length of straight lines, which is typically if we're thinking about the length of straight lines, we're thinking about the length of a line between two different points. So the way that you guys actually did this back in the day is you didn't call it the length, you called it the distance between 2 points. So if you guys remember the distance formula from like back in middle school, it was that the distance is the square root of the difference in the x coordinates of the 2 points squared, plus the distance between the y coordinates of the 2 points squared. And so this formula is based off of the Pythagorean Theorem, and it makes kind of like a triangle if you look at it, and the distance between the 2 points is like the hypotenuse of the triangle, which is why the formula looks like that. So back in the day, you guys would use this as the distance between 2 points, which we could also say is the length of the segment that connects those 2 points. So this is the distance between 2 points. Which is the length of the segment connecting the points. So we're not going to use this exact formula, but we're going to use this idea to find the distance of a curved line. So if you think about a curved line, let's say we have sort of like a parabolic shape here, just a curve going on there. If I wanted to find the distance of this part of the curve right here, I could calculate the straight line between those 2 points, and that would give me the distance between the 2 points, and it would be fairly close to the distance of that curved line, but it wouldn't be super accurate. If I wanted to get the distance of the actual curve, it might help for me to break this up and find the distance between this point and this point, the distance between this point and this point, the distance between that point, and so on, and then add up those distances, and that would be a little bit more accurate. This might feel familiar to when we first started looking at integrals, and we were talking about the area underneath a curve, and we broke up the area at first into like 4 rectangles, and then we started to break the area up into like 8 rectangles, 100 rectangles. The more rectangles you had, the more accurate your area was. And the same thing is what is happening here is the more line segments you have, the more accurate your arc length is going to be. So eventually what we started to say with the area underneath the curve is that we were taking these integrals where we were saying we had infinitely many rectangles, and then the area underneath our curve was starting to be an exact answer rather than saying we were approximating it. So what we want to do is the same thing, but with segments. We're going to say that the sum of an infinite amount of segment lengths will give us the length of the curve. All right, so we're going to go ahead and write down how we're going to find the arc length. So the length of that curved line. So if you have a function that is a smooth curve, and what I mean by a smooth curve is that it is continuous and it's differentiable. So if you guys remember, continuous graphs are ones where there's not a hole in the graph, there's not a jump in the graph, there's not a vertical asymptote. Differentiable means that there's no sharp corners. So it's a smooth curve that's continuous and differentiable, and this smooth curve that's differentiable is on the interval AB. So we have to have an interval that we're looking at to find the length, because if there's not an interval, then we don't know what piece of the curve we're looking at. So the formula is S equals, S is the variable they typically use for arc length for whatever reason. So you're going to evaluate the integral from a to b, of the square root of 1 plus the derivative of the function squared. And that's how we're going to find the arc length. So this formula that we're using right here, it can be written if the functions are in terms of x, as they typically are, but it can also be used if the curve is in terms of y. Oh, sorry about that. Okay. So for our first example, we're going to find the length of the curve y equals x to the third over 6 plus 1 over 2x. And we're looking at this on the interval from 1/2 to 2. So I know that for me to use this formula, I have to take the derivative of my function. So before I take the derivative of this function, I want it to look a little bit nicer so that it's easier for me to take the derivative. So I'm just going to write this as 1/6 x to the third because that's easier for me. And then this would be 1/2 x to the negative 1. So my derivative, 3 times 1/6 is 3/6, which is 1/2 x squared. Negative 1 times 1/2 is negative 1/2 x to the negative 2. So there's my derivative right there. And now I can go ahead and say my arc length is this integral evaluated from 1/2 to 2. And then I've got the square root of 1 plus my derivative squared. And we're going to go ahead and type that in like exactly the way that it looks. And just make sure that you're careful when you're typing things in so that your parentheses are where they should be and all of that stuff. So 1/2 x squared minus 1/2 x to the negative 2 squared. So I'm going to go ahead and write my answer as a rounded decimal to 3 decimal places, like we typically do. And then I'll go ahead and also write the exact answer as a fraction. All right, so the second example, we're going to find the length of y, not y equals. I switched this one up. All right, find the length of x squared equals y minus 1 to the third. And this is going to be on the interval from 0 to 8, where it's the x that's between 0 and 8. So this formula can go either way, this equation. You could do this one in terms of y or in terms of x, depending on which variable you chose to solve for. And I'm going to go ahead and do it in terms of y just so you guys can see the process for that, just in case it's ever a situation where you would like have to do that one or where it would be much easier to do it in terms of y. So for this one, first I'm going to go ahead and take my equation and solve for x. So x equals plus or minus square root of y minus 1 cubed. And another way to think of that is plus or minus y minus 1 to the 3 halves. Now, when I start to work with this, I know that I'm going to evaluate my integral, and now that my function is written in terms of y, my evaluating in the integral also is going to need to be in terms of y, so I can't use these x values of 0 and 8 in my integral. So I'm going to go ahead and plug them into the function to see what those corresponding y values are, because I'm going to have to use those instead. So 0 squared is just 0, and then I'll go ahead and cube root each side. So I've got 0 equals y minus 1, and so y equals 1. So that's the lower bound of my new interval. And then I'll go ahead and do the same thing with the 8. 8 squared equals y minus 1 to the third. So that's 64. And then I can go ahead and cube root that. And the cube root of 64 is 4. And so the upper bound is going to be 5. Okay, so that's what we're working with. Let's go ahead and figure out what the derivative of our function is. So now if we look back to our formula, we're taking the derivative and we're squaring it. So if you look up here, I've got plus minus. I don't have to worry about the fact that it's plus minus because if I use the positive version versus the negative version, the only difference is going to be that my derivative is going to have a positive in front of it or a negative in front of it, and it's going to be squared regardless. So that means that the positive and the negative aren't going to matter. So I'm going to go ahead and just do the plus version because it'll be a little bit easier. We're just going to ignore the negative. So I'm going to go ahead and do that. So for this one, I'm going to do the derivative of the outside function first. So I'll drop the 3/2 to the front and subtract 1 from the exponent, and then multiply by the derivative of the inside, which is just 1. So my derivative, pretty simple. You can write it as a square root if you want. 3/2 and then square root of y minus 1 if you think that would be nicer to type in. It's up to you. So now we'll go ahead and find our integral. We're evaluating it from 1 to 5. We're going to integrate 1 plus 3 over 2 y minus 1 to the 1/2, and then that is going to be squared. So I have from 1 to 5, I have the square root 1 plus 3/2 x minus 1 to the 1/2, and that is being squared. So the arc length is 9.073 approximately. And we're going to go ahead and do one more example. So this one is going to be to find the length of y equals ln of cos x on the interval 0 pi fourths. So first I'm going to go ahead and find my derivative. So the derivative of the outside function is 1 over what you're taking the ln of, so 1 over cos x, multiplied by the derivative of the inside function, which is negative sine x. So our derivative is negative sine over cos, which is actually negative tangent. Now technically you don't have to simplify this at all because you are going to be plugging in a calculator. So if you don't want to simplify that and you want to leave it as negative sine over cos, be my guest. So now I can go ahead and write my integral. I'm evaluating it from 0 to pi fourths. And I've got the square root of 1 plus negative tan x squared dx. And there is all sorts of simplifying you can do to this if you wanted to. You could say that 1 plus tan squared x is the same as secant squared. So this is really just taking the square root of secant squared. And then that is just secant, so you could evaluate that. However, ultimately I'm still going to be typing it in my calculator. I don't feel like doing it by hand, so I'm going to go ahead and just do that. So that's me. I don't feel like I need to simplify it if I'm going to type it in anyway. So I've got 1 plus negative tan x squared. So I'm making sure that my parentheses are where they should be so that I get that right. Got to make sure you're in radians, so don't write that answer down, that was wrong. Okay, so my arc length here is 0.881.